Welcome everybody. This is Todd Roberts from SenseMetrics. We want to welcome everyone to this live webinar. We're presenting the case study of Yeager Airport. We'll be featuring Measuran's shape array sensor technology as it relates to SenseMetrics cloud technology. And I'm joined with a friend and colleague, Jeff Barrett, president of Measuran. And both of us have support from our technical resources. I'm joined by Nate McGee, our technical director, and Jeff is joined by his colleague, Shane Spinney, works for Measuran. So we're going to have a very interactive experience here. Jeff and I will do most of the talking. We are live, so this is a live webinar. We'll have a few opportunities to address questions that come in throughout the presentation. There'll be a period where Nate and Shane will join us about midway through the presentation to address some questions that have been submitted, and then we'll hold a more formal question and answer session at the back end. All the audience members can submit questions by typing in a question privately or into a group format where everyone can see the questions in a panel on the right of your screen. And then after the webinar is over, we'll be sending out individual emails with additional resources and responding to questions directly as follow-ups to the webinar. First, we're going to cover introductions to Jeff and I. Again, I'm Todd Roberts. I'm the Director of Infrastructure for SenseMetrics. I have about 20 years of industry experience, 15 years of which has been practicing as a geotechnical engineer and geologist. During that 15-year stint, I was able to build up an instrumentation division at the engineering company I was working for, where I delivered design and monitoring services over several years in the Rocky Mountain region. The last 5 years of my career has been focused on the manufacturing side of things as it relates to monitoring, and currently I manage the infrastructure vertical for SenseMetrics. Jeff, why don't you introduce yourself?
Good morning and good afternoon, everyone. It's a pleasure to be presenting this webinar today alongside Todd. My name is Jeff Barrett, and I'm the president and geotechnical engineer at Measuran. And prior to joining the company, I worked for 11 years as a civil and geotechnical engineering consultant, working in the mining, dams, and infrastructure sector. And my experience was mainly in the design, analysis, and inspection of large civil structures.
Thank you. So a little table of contents here. We're going to cover the introductions. We're well through that already. Then we'll do an introduction on SenseMetrics technology, followed by SenseMetrics technology. Then we'll dive into the case study. We'll address installation and some of the data that's been collected to date. And then we'll review some of the lessons learned, which is largely from input we've gathered from some of the design team that are sitting in the audience here. Lastly, we'll address the question and answer session that we discussed earlier. Jeff, why don't you take over?
So I'll give a quick overview of Measuran as a company, as well as the shape array product line, to give a foundation on the technology before we jump into the case study. So Measuran is based in Fredericton, New Brunswick, on the east coast of Canada, founded in 1993 by Lee Danish, who was an MIT grad. Over the last 15 years, we've focused solely on the shape array product line, and that continues to be our sole focus of all current research and development and engineering. We've sold over 150,000 meters of the shape array products worldwide, and we hold over 20 patents, including a recent patent on the new cyclical installation method. And we distribute the product line internationally through 19 different distributor partners, covering over 30 different countries. So getting into the fundamentals of the product and technology, the shape array comes fully assembled and calibrated on a reel. These products are made to a custom length based on the user's requirements for the specific borehole installation. Every instrument consists of rigid segments with boards containing MEMS accelerometers and temperature sensors. The rigid segments are connected with flexible joints, which can bend in any orientation, but are resistant to twist. And we do our own in-house calibration of the triaxial MEMS accelerometer, and this allows us to achieve a field accuracy of 1.5 millimeters over a 32-meter length. And because we do our own calibration, we have built-in temperature corrections for a temperature range of minus 35 degrees to plus 60 degrees Celsius. So we'll go through the different installation methods. And again, because we use a triaxial accelerometer, the instrument can be installed in different orientations depending on what needs to be measured. So starting on the left-hand side, we have the typical vertical installation. The figure is depicting an installation in larger diameter conduit using our patented cyclical installation method. This allows for direct retrofit of an inclinometer casing, and our software will calculate the center of the casing to map deformation. The vertical installation can be installed in casings of 27 millimeters up to and including 100 millimeter inside diameter. We also allow horizontal installations where the shape array is rolled out horizontally along the ground surface or along the crown of a tunnel. And this allows for direct measurement of heave and settlement. And finally, we can install in an arc configuration to measure convergence, the inside of a tunnel or conduit or culvert, for example. And in this mode, our software will determine what accelerometer to take readings from based on the orientation of the sensor, whether it's near vertical or near horizontal. These photos show common installations. So starting on the left, we have a vertical install where two employees are unrolling the shape array into a pre-cased borehole. In the center, we have an installation for a rail monitoring application where the instrument is installed in 1-inch diameter casing and attached to the sleeper ties to measure settlement of the railway. And then finally, we have a shape array pre-installed into a 1-inch diameter casing being installed in convergence in the inside of a tunnel lining. Go through quickly the 3 different products. All products contain the same triaxial MEMS accelerometer, and we're simply packaging them different for different installations. So the SA-X model is purpose-built for horizontal installations, and this contains segment lengths of 1 meter. The SA-V is our most common and versatile product and can be installed in vertical, convergence, or horizontal, and is available in 250 millimeter and 500 millimeter segments. And then finally, the SA-Scan is our most durable and robust product, and this is designed specifically for repeated use for scanning the alignment of boreholes.
Now we're going to climb into the SenseMetrics technology stack. A little bit about SenseMetrics. We're currently operating on 4 continents, and we have physical offices in San Diego, California, where we're headquartered, as well as Denver, Colorado, where I'm based. Both offices allow us to continuously develop and maintain our hardware and software solutions. SenseMetrics operates in many industry verticals, ranging from transportation, such as the Yeager airport that we're talking about here, water resources, mining, construction, energy, and oil and gas. With a strong global network of partners, SenseMetrics provides various monitoring solutions to hundreds of owners and operators and engineers, as well as specialty consultants that have hosted over 300 million observations on our platform to date. Now I'd like to introduce the actual platform. The SenseMetrics platform consists of an integrated hardware and software pairing that delivers a true end-to-end solution by supporting a wide range of sensors on a single pane of glass. SenseMetrics offers a turnkey solution by delivering plug-and-play connectivity for sensors and devices, such as vibrating wire interfaces, using our pre-configured thread edge device shown in the white data collection boxes on the bottom of the screen there. Or any device, the thread can also serve as a gateway device, or for any device connected to the internet, and is delivered with everything you need to automate a wide range of sensors. It includes technologies such as mesh networking radios and cellular modems, a rechargeable lithium-ion battery, surge protection on the import ports, onboard storage for when connectivity is disrupted, support for various sensor and device protocols, and even accept secure firmware updates using over-the-air techniques. The platform can also support other gateway devices, which furthers user experience by providing flexibility. This IoT ecosystem allows for bilateral device control and subsequent data management of stored raw data, all backed by our secure cloud platform. In addition, the analytics engine delivers solutions that allow users to engage with various functionality, such as the reporting module or analysis tools and more advanced features delivered as what we call productivity applications, all depending on project needs. And we'll explore some of these together as we go through the presentation. In order to deliver this seamless experience, Sensemetrics has aligned with many industry standard sensor manufacturers. This allows the owner and his engineering team to design and deliver a monitoring program that is customized to project objectives. For Yeager Airport, the engineer relied on many sensor types, such as MEMS and vibrating wire sensors, manufactured by Measurand, which is the focus of this presentation, but also Geocon and RST. This strong partner network enables projects to quickly adjust to changing project needs by adding supported sensor types to the monitoring program that were otherwise unforeseen during the design or construction phases. As we drill into the Measurand shape array, we can see an illustration here in this graphic that shows how the shape array sensor can be automated, powered, and controlled using Sensemetrics thread devices. The plug-and-play nature between the SAA sensor and our thread allows the user to effortlessly automate any shape array and quickly log into the Sensemetrics software to manage map views, view graphs, manage reading frequencies, set alerts, and more advanced features from any internet-connected device. One of the unique things that Sensemetrics is able to provide to the industry is our strong relationships with our partners. I want to ask Jeff to kind of speak to some of the innovative solutions we've launched together and how we change sort of the way people monitor in the industry.
So I wanted to spend a few minutes talking about the Sensemetrics integration because it's the most advanced integration with any software or hardware company that we've done to date. So a shape array outputs data that's a little bit more complicated than a traditional, let's say, vibrating wire sensor that just needs a few coefficients to calculate engineering units. So because we do our own calibration, each shape array has a unique calibration file, and it is required that the raw data is fed into our conversion software, which contains our proprietary algorithm to calculate engineering units from the raw accelerations. So the goal here was to create a seamless user experience. So the integration consists of two different components. The first component is the retrieval of the calibration file. So once a shape array is plugged into a Sensemetrics thread, the thread will automatically detect the serial number of the instruments and then pull the appropriate calibration file from the Measurand FTP server. So this reduces the risk of making an error in transcribing calibration files, for example, and ensures that you always have the right calibration file for the instrument installed. And then the second component is converting that raw data into engineering units. So instead of having to run a separate conversion application to convert that data, what we've done is packaged up this algorithm and allowed Sensemetrics to deploy it in our cloud software. And this allows the user to simply log into the cloud platform, open an XY deformation plot, and this conversion process from raw data into engineering units is done on demand and on the fly. So every time the user logs in, within seconds, the raw data is converted without any additional user intervention.
Thank you, Jeff. And we'll kind of wrap up the Sensemetrics technology overview by exploring some of the software features that we have. On the software side of things, authorized users are able to build their own monitoring environment using what we refer to as core applications, the icon shown on the left in green here. These day-to-day tools range from GIS mapping interface to various graphing tools to document control and alerts, where users can establish up to 4 alert levels or thresholds. Data tables allow users to access data importing and exporting functionality, and the revision management tool is a software feature that establishes Sensemetrics as a system of record, providing tools to catalog system changes and necessary modifications that are made to sensors and devices, but only by approved and responsible users. In addition to the core applications, Sensemetrics has developed more advanced software functionality for targeted markets that require specific workflows and/or tools using what we call productivity applications, shown on the right. The two productivity applications that the Yeager project team uses and still uses today are the report module and the deformation monitoring module. And I'll give examples of these later on. So now we're going to take a quick second to pause. Hopefully there's been some questions submitted, and I'd ask Nate and Shane to kind of respond to a couple of them.
Great, we have had a few great questions in the chat that we'll just start off with. The first one that I'd like to address is a question about whether or not any other data loggers are required if the shape array is used with a Sensemetrics thread. And the answer is no. If you're combining measure and shape array instrumentation with Sensemetrics logging platform, all you need is the thread for the logger. There's no extra logging equipment required.
Excellent. I think another question that came in was, do the threads store data? For some reason there's telemetry interruption. Can the thread store the readings, or are they lost? Great question. And actually, if telemetry is broken for whatever reason, the thread can reliably store that data on board the device. And whenever the cloud connection is restored, all of that data is synchronized with Sensemetrics, so no data is lost.
Shane, do you have another one?
Yes, sorry. I was just picking a question out here. There's a couple of really great ones. The next one is one that maybe Jeff would like to address, and it is, can you install a measure-and SAV in the same borehole as a vibrating wire piezometer?
Yes, that can be done. It's largely dependent on the inside diameter of the casing, but using the cyclical installation method, if you're direct retrofitting an existing casing, for example, and the casing diameter is large enough, there'll be a void space that you would be able to snake in a vibrating wire piezometer. Oftentimes for new installations, what's done is the vibrating wire piezometers are attached to the outside of the casing, and then the fully grouted method is used if that's applicable for your soil conditions.
Excellent. Another one we have here is, what is the min-max reading frequency of the shape array when reading through the thread? The max frequency that you can read a shape array is every 5 minutes, and the least frequent that you can read is once a day, so once every 24 hours. And that's all just set by the user through the application and can be changed at any time.
Thanks, guys. It sounds like you have some more questions, so let's hold some of those for the back end of the Q&A session, and we'll just carry on with the case study here. First, we want to introduce the background about the project. The location of the project of the Yeager Airport is Charleston, West Virginia. It's an airport that experienced a slope failure, and a retaining wall was built to restore grade. And the part of the airport that was impacted was runway 5. The owner is the city of Charleston, and their selected engineer of record is Schnabel Engineering, and I believe some of the engineers and the contractors may be on this call, so I'll try to behave myself here. And the features that were delivered as it relates to monitoring of an 85-foot hybrid, 85-foot high hybrid retaining wall, and the focus around the instrumentation was an instrumentation program that handled before, during, and after construction activities, and continue to today. And the geostructural monitoring that was selected consisted of shape arrays, which again is the focus of this presentation, but also included vibrating wire sensors such as load cells, strain gauges, and multi-point borehole extensometers. And then NSAR was also used to look at the sort of the overall footprint of the airport for deformation monitoring. So now we're going to focus on the event to put perspective on this project of why it was so important. Basically, the event that occurred did impact the airport. Early in 2015, the EMAS portion of the runway, shown on the bottom left, developed significant surface cracking. The EMAS is sort of an aviation sand trap of sorts, for airplanes, designed to stop aircraft that do not take off in time. From the picture shown here, we can see that the EMAS structure is particularly important for this specific airport as grades drop off steeply at the end of the runway. As time progressed, the surface cracks gave way to a deeper slope failure, which impacted not only the runway itself, but also structures at the toe of the slope. It even blocked a nearby stream, which redirected surface waters into the residential and commercial properties shown below. So what challenges faced the owner and the engineer to come up with a solution to restore the airport? Well, first and foremost, it was an active airport. Keeping the airport operational was important to the community and the city. Of course, it's all revolving around safety, which kind of impacts every element here. One of the major elements to tackle first was the active slope failure. This required stabilization of the unstable terrain prior to wall construction. The site access was challenged due to the grades. There was hairpin turns, single vehicle lane access, and then steep grades, all being overridden by soil that was moved recently during a slope failure event. Other challenges they faced was weather delays. I believe the first construction season they had rain every single day during the summer, which slowed down construction progress. And there was even a planned winter shutdown that was between the first and second construction seasons that was planned, but also caused weather-related delays. As we touched on slightly in the site access portion of this slide here, there was a restricted working area. Working benches, for perspective, were about 15 feet in width, and this required a lot of orchestration between the contractor and the sub-trades that were working on the project site. For example, large drill rigs drilling large diameter shafts were readily installing soldier piles. There was tieback anchors, there was man lifts and forklifts mobilizing around the site, and they all had to be orchestrated due to that. .15-foot working width. Another thing that had to be remedied up front for a lot of different reasons, but also to facilitate construction operations. As I alluded to, every one of these challenges was ultimately impacted to a certain level of safety, and the contractor and the engineer had to work hand in hand to relieve those safety pressure points and provide a safe working environment for the workers as well as asset holders around the project site. So what were the solutions? Well, on the design side, Schnabel Engineering designed a hybrid retaining wall to restore the EMAS at the end of runway 5. I don't want to pretend to be a geotechnical engineer right now, but the retaining wall consisted of a sort of a drilled soldier pile at the face of the wall and dead man soldier piles behind the wall. These two rows of piles were tied together using tie rod reinforcement. And then lastly, a concrete cap beam was constructed sort of in the middle of the wall to tie the lower and upper wall elements together. The wall was also instrumented during construction using a combination of sensors that I'll describe on the next slide. But before we go to the next slide here, we can see 3 shape arrays. The design intent was to have 3 vertical shape arrays down the wall face, and then they would be automated using threads installed at the bottom of the wall. We'll address some of this later on in the presentation when we get to the installation conditions. Another part of the solution was the monitoring scope. On this particular project, there were various technologies used. There was 20 devices being threads and vibrating wire interfaces. These were used by provided by Geocon. There were 456 monitoring points deployed throughout the project site. There were 3 monitoring technologies utilized and over 8.5 million observations to date, excluding the data collected by the NSAR program that I'll describe briefly here in a second. We alluded to the threads shown on the left here and the LC2 devices that were reading vibrating wire sensors. And then we use MEMS technologies as well. And there's 2 different models of shape arrays. Jeff, would you mind sharing with the audience why there were 2 different models used?
The initial 2 SAF were installed as part of the ongoing embankment monitoring. And then during the design of the retaining wall, Measurand developed a new product, SAV, that's based on a triaxial higher accuracy accelerometer. So during the construction monitoring, the new SAVs were installed as part of the ongoing monitoring.
Thank you. Schnabel Engineering also called out other sensor types. For example, Geocon's vibrating wire sensors consisted of load cells, strain gauges, and extensometers. They also used RST vibrating wire load cells that were all interfaced with vibrating wire logger devices from Geocon. Lastly, Schnabel wanted to look at big picture type monitoring, so they relied on NSAR technologies delivered by Ovella, also known as Scylla. This company was able to provide ground deformation monitoring across the whole footprint where sensors were, as well as where sensors were not installed. So now we're going to kind of take on the installation of the project. As we go into this installation, Jeff and I will tag team through some of these photos, and the first slide here, Jeff's going to speak to.
So the first photo shows an SAV being prepared for installation. You can see it's being installed on a spool, and the first segment is starting to come off the reel. The second photo, you can see segments being unrolled from the reel, and then finally in the photo on the right, you can see that someone's on top of a scissor lift installing the shape array into the casing that's installed on the pile. So you can imagine that if you were trying to do a complex installation in this environment, assembling parts at the top of the pile, it would be, somewhat cumbersome. So this is a great application for the shape array that comes to site pre-configured and can simply be unrolled and deployed into the casing.
In this photo here, we're looking at some of the conduits and casing that was installed to the soldier pile elements. And Jeff, I'd ask you to speak to the sort of the challenges that arose here at this part of the project.
So when we started chatting with Todd about the construction and sequencing of this project, we determined that it was being constructed in two stages. So there was an initial lower wall that would be backfilled, and then construction of an upper wall. So because the shape arrays are constructed to a single length and couldn't currently be field adjusted in length, we had two options available to us. We could construct the shape array to the ultimate length and then store the unused segments at the top of the first pile. That posed a bit of a logistical and also health and safety issue, having this large reel stored at the top of a pile while they were backfilling. So it was decided to manufacture two separate instruments, one that would go in the lower wall, and then that would be backfilled. And then once the piles for the upper wall were installed, the second shape array would be installed on top of that.
And as we can see in these photos here, we have two different size conduits. On the left, there's a larger one. I believe it's 4-inch diameter PVC conduit. And that was sort of cable management conduit. Vibrating wire sensors and shape array sensor cables all travel down the conduit for nice cable management, as well as protecting the cables. And then the smaller casing on the right is the casing for the shape array. In this case, I think it was metal or steel 1-inch conduit piping that was used for the shape array, and that was also attached to the same pile. All devices then exited the bottom of the conduits and then connected to either threads or vibrating wire interfaces. This slide here continues the conversation around the selection of two shape arrays. And Jeff, if you could speak to the overlap of the shape arrays and some of the reasoning behind that.
So you can see the photo on the right. You have the upper shape array coming through and overlapping by 1 meter with the top of the bottom shape array. So obviously this was done for logistical reasons, but in terms of data interpretation, when looking at cumulative deformation, we'd like to have that 2-segment overlap so that the cumulative deformation of the bottom shape array can be applied as an offset to the top shape array. So I'll point out at this time, this was required when this project was taking place. However, Measuran's currently working on a connectable shape array, which will be released later this year, and that will allow additional sensorized segments to be added in the field. So this would be a great application for that new product.
And finally, this photo here kind of shows the wall face at full completion at full height. And as you can see here, we have 3 sets of conduit running up on the left, middle, and right of this picture here. And each of them sort of have the same sort of condition. There's a larger 4-inch diameter cable management conduit that runs up the wall, and behind this wall face are extensometers in the soil backfill zone. There are strain gauges on the tie rods, and then there are load cells, one of them shown here in the photo on the sort of the left bottom part of the picture here. A load cell is installed on the tieback elements, and all those cables ran into the large diameter conduit. The shape arrays ran up the outside of the soldier pile wall, and you can see here that it's hard to see, but you can see the 1-inch conduit running up on the second one. At the top, there's a NSAR reflector, and all the sensors kind of ran up and down the wall, either on the wall face or behind the wall. And this gives us a good opportunity to explore some of the interim construction phases. As you guys saw in this photo on the left previously, the unrestrained portion of the soldier pile was standing up in the air, unrestrained for several weeks, probably even months, before it was actually completed as an intact wall. And some of those heights range from 40 to 60 feet above grade. And as we could see in the data shown in the graph view here, the delta X and delta Y plots in inches, there was several tenths of an inch of deformation, sort of a wiggle effect of the pile as it reacted to wind loads, vibration, and other forms of deformation that would cause the pile to move. And this was anticipated behavior. We're just able to capture it. And Schnabel was able to look at this information live with the owner and make construction level decisions in a real-time manner. And then, of course, this is kind of a photo at the end of construction. There's enough time for the seating to take hold, so it's well vegetated. And the wall completed in, I believe it was fall of last year. And the airport and Schnabel Engineering are continuing to monitor the wall with all the sensors that are installed for several years in the future. Now we're going to climb into some of the data that's been collected to date. In this picture here, we're looking at our map view. In the map view, the spatial view allows for different map format views. This one happens to be what we call the map view. And in this view, you're able to set up a base map. You can use preloaded Google or Esri base maps. You can also load in your own images as base maps. And you can add layers on top of it, which in essence makes a GIS interface where you can, in this case, Schnabel added some topographic grade plan lines as well as the sensors. The sensors that are shown here are the shape arrays. You can see them as color-coded dots sort of in the middle of the aerial view. And this is actually using our deformation monitoring module. This allows for color-coded visualization of the shape arrays that shows you the last reading in terms of deformation. The color coding reflects to different levels of movement set by the user. And then there's vector tails also put on the color-coded sensor icons that show you orientation and qualitative magnitude of movement. Then the user has the ability of toggling on and off a time series graph shown on the bottom right here. In this case, we're looking at 2 weeks of readings, and you can toggle on and off the sensors you want in the view, and you can quickly co-locate everything in a single glass of paint. The spatial feature also offers the ability of loading in images. In this case, Schnabel wanted to load in one of their design cross sections of the wall face. And then they've co-located all the different sensors on the wall face that are also color-coded, in this case, for different status conditions. Blue icons, as shown here, represent low power mode, which means they're being turned on for reporting at a certain interval. I'm not sure what it was here on this job, but in this case, this preserves battery life on the threads and it's a form of power management. Other colors that may appear are red if the devices are offline for any reason, and then you can drill into SenseMetrics diagnostic tools to troubleshoot remotely as to what the problem may be. Or in more common situations, they turn green, which means they're actively taking readings. As we move on to the data, one of the important graphs that we have here is the XY plots. And this is a way of depicting inclinometers, both IPIs, manual inclinometers, as well as shape arrays. In this case, we're looking at a shape array, and we're looking at about 15 consecutive readings in 2019 to 2020. And we're looking at the deformation in terms of inches. You can plot them against elevation or depth on the y-axis. And you can also co-locate the various thresholds that are set by the user. But this is where we got to look at some interesting information, and this is courtesy of Schnabel Engineering. This is sort of the story of two SAA segments, as I'm calling it. And this story speaks to how Schnabel wanted to look at two specific segments on the shape array that were next to a tieback anchor. And they wanted to see how those individual segments reacted when the wall face was stressed, when the anchors were stressed and or backfilled, and see how the wall deformed in reaction to those events. And I've sort of made a catalog here of what occurred. Going from left to right on the upper graph, we can see two anchor stressing events. The first one occurred on August 22nd, where there was about 1/2 inch to 3/4 of an inch of contraction as the anchors were stressed and the wall compressed back in. And there was another event similar to that on September 7th. Then time was carrying on, and around October 18th, there is what has been described as sort of a contractor milestone, and basically that's a nice way of saying the contractor or one of the subtrades accidentally hit the shape array casing and displaced it by about 2 inches. In order to respond to that contractor milestone, Schnabel made the informed decision after inspection and verification that it was a contractor-derived event to reset the baseline, just to reset it back to 0 on October 19th. Then as time went on, you can see November all the way through March and April, there was very little activity, if any at all. But then in the middle of April, going into May, the contractor resumed construction activity, and you can see an expansion of the wall face, albeit 1/4 of an inch or so, that was related to wall backfilling operations. So this plot, using two individual segments of the shape array, was able to tell a very specific storyline as it related to construction observations. Also, what we can see here on the bottom of this graph is a temperature plot that's synced with the same time series interval that we're looking at here. You can plot all different metrics together. You can plot SAAs versus temperature. You can fold in rainfall. You can look at piezometric pressure, and you can establish graphs that really show cause and effect relationships that allow the user to quickly make decisions based on the real-time data that's feeding into the platform. On the data table side, Schnabel was a big fan of using some of this feature. This enabled them to export the raw data that was collected by Sensemetrics. And this could serve many purposes. One is to use it as a data historian type application where the data that's collected can be uploaded to a third-party server for compliance for the owner's requirements. Or you might want to use third-party software programs to do analysis or quality control on the data that's being collected. And this here, we're showing strain gauge information, but maybe Jeff, you can talk to how shape array data can be exported from Sensemetrics and analyzed within Measuran's own software suites.
Sure, Todd. So it's always best practice to store the raw data, really for any sensor. So because Sensemetrics does the on-demand conversion, the raw data from the shape array is always preserved in their cloud platform. So this tool allows you to export all of the raw acceleration and temperature data into a CSV file. And that CSV file can be used in any of our SA Suite software. So if you need to do additional diagnostics in our data checker application, for example, it's easy to do that. Or if you wish to load the file into SA View to look at some of the additional analysis and diagnostic tools there, gives you the ability to do that. It also allows our support team to use software that we're more familiar with if the client needs any help with data interpretation.
Another feature that was used at the airport is the alert feature that Sensemetrics offers, and this is an example of a alert that was actually set up at Yeager. And in this, I'm going to kind of walk you through this dashboard here. So this particular alert, you get to create a new alert and get to name it at the top. This one's called SAA Threshold 1. Moving to the right, you're able to set the priority: low, moderate, high, or critical, 4 different levels. Then you get to set the sensors that are tied to this alert. In this case, 37 segments of the shape array are associated with this alert. Moving down in the view, you'll see triggers. There's 4 of them that were set. You can add as many as you need to. In this case, we were plus or minus an inch of deformation of delta transverse and longitude. And then you're able to toggle on or off functionality like alert verification. That feature allows the user to have sort of false alarm avoidance strategy where you have to have 2 consecutive readings exceed a threshold before an alert goes out. That cuts down on maybe birds landing on a sensor or construction equipment causing an alert to go out as a vehicle drives by a sensor during an active reading. Then we're able to establish trigger actions. Some of the actions could be to send out an email or text message alert, and you can add recipients. You can add within your company, or perhaps the contractor or the owner himself can all receive alerts depending on how the user configures this portal. And then you can also enable different actions. Some actions could be to change the sampling rate. As Nate said earlier, and to answer one of the questions, you might have a reading program that calls out for shape arrays to be read once or twice a day. But if you have an exceedance of a threshold, you can change that autonomously to every 5 minutes or every hour to get data fidelity when you need it most, when things are moving, and not have excess data when things are not moving. Other features you can enable here are the ability to toggle relay devices. Examples of that are turning on and off a siren or a beacon. It may be controlling things like pumps and flow meters so that we can control the cause and effect relationships of a different monitoring application. Lastly, one of the popular features that's sort of a SenseMetrics fan favorite is our report module. This feature allows you to create user-defined preset reports that are delivered on a scheduled interval. In this case, you can set up your, I made a sample one here of a weekly report where you can set the, share this with different users. You get to customize the report by setting up your settings, such as the time zone and the language you want it issued in. You can create a cover page with a title and project name and author. You can add contact information, even a logo, and then you can add sections. Some of the sections that can be added vary, but they can be really customized to the project need. They could be alert trigger histories, graphing, whether it be XY graphs or time series. You can even do more advanced things like polar graphs, which are used to look at wind speed and direction. You can add images and even add custom notes. Then once you're done configuring your automated template of how you want your report to appear, you can go to the report scheduler on the left and you can enable or disable it. And then you can set it to different daily and weekly and monthly behaviors. And then you can pick the day and even the times that you want it delivered, and then schedule the people that it's delivered to. This feature is very common on our projects because it takes the monotony out of custom printing from Excel and other documents into PDF and assembling your own report, but rather use the SenseMetrics analytics engine to pre-configure and set those features. So now we've kind of talked through the installation and the data that was captured from Yeager Airport, and we're going to want to wrap this up with a little bit of lessons learned. Some of this and most of this is through the eyes of the project team, so I'm just going to try to articulate some of this to the audience here. One of the important features learned on this project was the ease of install. Having access to pre-configured devices like threads that can automate equipment quickly and efficiently is a very powerful value to a project. It saves on upfront costs. It also eases the steep learning curve of projects that have complex solutions that may exist. The use of a plug-and-play sensor like a shape array with a thread provides value as the ease of installation. And you couple that with the unique integration of SenseMetrics and Measurand, where you can automatically upload calibration files in a matter of seconds, just makes the whole experience much more efficient and enjoyable. All this together leads to a quick uptime. I think if you ask the people that were involved in the installation, they'll, going back a couple of years here, they're probably gonna say less than an hour, but it's more likely 30 minutes to automate a shape array once the shape array is installed inside the casing. Another lessons learned is that automation provides extremely valuable insight to structure performance when you have access to the real-time data. This is particularly true when you're looking at active construction jobs that are working in a dynamic and or high-risk work environment. And I think many of the folks that worked on Yeager Airport will attest to the fact that this helped them proceed in a more safer manner and make decisions in a real-time environment based on the system that was used. Some other values that the system provided were shape arrays allow the designer to evaluate both the anchor stressing and wall backfill operations as it relates to design tolerance of the wall, and they were able to compare the actual movement of the wall to that of the anticipated theoretical movement of the wall. So part of the component was at the front end was the engineer wanted to be able to evaluate cause and effect relationships based on the design behavior of the wall itself. Also, another value here is having a single platform to connect all different sensors enabled the consultant, the contractor, and the owner to see access to all the real-time data on a regular basis, day or night, around the clock. It was always there. You didn't have to do manual interventions to collect data. It was just always available. Something learned on the front end, this is through Schnabel Engineering, is that they were weighing the options between a manual inclinometer probe versus automation of an IPI or shape array probe. In this case, there was significant safety concerns about sending crews out to do manual collection of inclinometer data. And even if they were able to do it, they were inaccessible at various stages of construction, which would create large data gaps for manual collection techniques. With the use of the shape array, they were able to collect 0.5 meter segment spacing on data fidelity or high resolution deformation monitoring on the individual soldier pile elements at predetermined regular intervals, and then compare them with observations by the contractor and inspection crews. And I think that kind of wraps up our lessons learned. So now we're going to open this up to questions and answers. I'll invite Nate and Shane to provide some question and answer responses.
Great, thanks, Todd. Lots of great questions coming in. The first one, maybe Jeff would like to field, and it's kind of just what the principal difference between conventional and in-place inclinometers relative to the shape array.
Sure. So, there's several differences, but maybe I'll just focus on, application for this project. So, installation, being key here. You don't need to assemble the different IPI rods to install them. So you can see that would have been a bit tricky on this site. And then the other key difference is spatial resolution. So we used a 0.5 meter segment length on this project. And from a price point of view, a 0.5 meter IPI would have been, quite expensive to instrument the same length of shape array here.
Great. Another question we had was how long does it take to install a shape array and see live data from the thread? I can address this. A 50-meter shape array can easily be installed by a couple of people within about a half an hour in the borehole. And as far as getting live data from the thread, that happens pretty much instantaneously. It's pretty much plug and play. You plug it into the thread device and configure some settings, and you'll have data almost immediately. So from start to finish, easily have it done probably in about 30 minutes. Another great question we had is one for you, Todd. Can you describe if there's any radio frequency limitations that would cause communication issues with threads?
Well, there are sources of interference that can exist on project sites, but the thread radio system is sort of a dynamic multi-hopping radio signal that's embedded with the mesh radios that we use in our devices. So the threads will automatically search for each other and optimize to the optimal reading frequency, radio frequency to maintain connectivity.
Great. Another question we had that came in was whether or not the SA inclinometer casing needs to be anchored to bedrock or a more stable foundation. Jeff, would you like to address that one?
Sure. So the same principles of, manual inclinometry would apply to shape arrays. So you need to have either a stable reference end, so that reference end needs to be in bedrock or stable soil that's not moving, or you need to monitor one of the segments on the shape arrays. So as an example, a prism has been installed at the top of the shape array, and that deformation data has been used as an offset for one of the segments. But essentially you need to have some reference, either stable or measured, in order to look at cumulative deformation.
Great, thank you. Another question we had that came in was whether or not there was any wheels or special attachments required to install a shape array into inclinometer casing. The answer to that is no. Shape arrays don't rely on the grooves in the inclinometer casing for orienting the data. Every shape array is calibrated at the factory to a physical X mark that's on the instrument, which will determine the direction of the positive X axis in the data. Once we have that installed, we can measure a simple offset with a protractor on site and apply that offset value to the software, and it will reorient the axes to the desired direction for the data.
Shane, I think we have a couple more minutes for maybe one or two more questions before we run out of time here. Or do you have any others that you want to throw at us?
Sure, we'll finish it off with two final questions. The first of which is for you, Todd. Just a question about SenseMetrics systems. Are they a mesh or a star system?
SenseMetrics currently operates with mesh radio technologies, although we are working with some star topology systems using devices that allow us to pull in star topology radio technologies.
Great, and I'll finish off with one last question for Jeff, and just a reminder to everybody, if we didn't get a chance to answer your questions, we will follow up with you directly after the webinar and address your questions. So Jeff, the question that I'd like you to address is, in an earthquake area where an instrument is set up for long-term monitoring, how frequently does the equipment need to be recalibrated?
So the MEMS themselves don't require recalibration. That calibration process that we do is for the life of the instrument. The only time we would require a calibration check, if you will, is if the instrument is being removed and reused on a project multiple times. In some instances, clients send them back to be, basically have the calibration verified by the factory, and we'll reissue calibration certificates, but under normal use conditions, it's not required to be recalibrated.
Okay, well, thank you, Shane, for walking us through some of those questions, and Jeff, thank you for your time with the answers. And we want to thank everyone for joining us. We hope everyone found value in the Yeager Airport case study that we presented here. If you have any follow-up questions, feel free to reach out to the team. We have Jeff and my emails here on the screen. You can also reach out through the GoToWebinar platform to reach us as well. Thank you, everybody, and have a great day.
Thank you.